So our first stop on our virtual field trip into the Berkeley Hills is of the oldest unit in this section in Claremont Canyon. So this is the upper part of the Claremont Formation. As you can see here, sort of contrary to the traditional model of original horizontality, we have beds here that are actually pretty steeply inclined, as you can see here from Zamana's scale. These beds were originally deposited horizontally and now have been uplifted and tilted actually beyond vertical, so they're now considered overturned. As we're going to be going up close here in a few seconds, we're going to be evaluating these different layers of sedimentary units here. Just taking a look back here, we can see that there's these prominent sort of yellow-orange beds, and there's these smaller gray beds that are obvious in outcrop here, and we're going to go up closer to explore and look at these to see the various lithologies that are exposed here in Claremont Canyon. But the big takeaway here that I hope to impose upon all of you is just sort of the scale of the outcrop, and also to get a sense for the dips of the beds here. As we can see from our understanding of right-hand rule, the beds would be dipping away from where Zamana is looking currently, so in this direction if we were using our right-hand rule method. But let's go up closer to get a better view of the actual rocks themselves, to see that layering that could be informative of where these rocks formed. Okay, so now we are at the outcrop here and looking at these different colored units here. So we can see sort of obviously to my right here, these dipping beds. And as we noticed from across the street, there's sort of this layering here where these orange and yellow units are eroding out differently than these sort of darker, more fissile or crumbly units here. So coming up to this outcrop, the first thing that I would do is to actually break off a piece of this rock. So looking at this thicker unit here, we can see that there's quite a bit of a difference in terms of thickness between this less resistant rock and this more resistant rock here. So if we actually break off a piece here, we can see that this rock is actually fairly hard, and there's some layering into it very subtly that's also exposed here, showing the original orientation of the bedding. And what you can see here is that this rock is actually quite resistant. It takes quite a bit of hitting to break it up, whereas this unit here is quite fissile. It's very easily broken apart by my rock hammer, demonstrating that there's quite a bit of a hardness difference. And if I actually come and grab a piece of this shale unit here, we can actually take a sample and see that it's actually very fine grained. So if I were to actually take this and look under a microscope, or even look under a hand lens, we would see that this unit is very fine grained. And if we think back to what we learned in the sedimentology lab, we can think about this in terms of energy environment. So both of these units, both this green unit, or this yellowish unit, and the darker brown shaly unit, had to have formed in a low energy environment. You don't see any obvious large or coarse grains here. You might see a few beds that are a little bit coarser, indicating maybe a shallower environment. But what we can infer from looking at both of these units is that this had to have formed deeper in a marine environment, so in like a near shore type environment. And this harder, more resistant unit here is what this unit's actually named after. This is the Claremont chert. So this is chert, and if you think back to what we discussed in both lecture and in lab, this unit forms, this lithology forms as a result of tiny organisms, in this case what are known as radiolaria, which are microorganisms that form their shells out of silica. When they die, they rain out of the water column and are deposited as what's known as a siliceous ooze. And over several thousand and millions of years, you get this repeated layering of nearly pure silica that's the result of these small microorganisms. And now we know that here, when we're looking at this section, this is a dominantly marine section. So these rocks had to have formed in deeper water with calmer energy environments. And a big thing to take away here is just the deformation features as well. Just for interest, we can see how these beds have been sort of sheared and tilted and bent due to tectonic regimes that have tilted these things up. And in a second here, we're actually going to walk over and just look at a small scale fault, which is pretty evident in this outcrop. But a big takeaway here is just to see that there's actual variation in the bedding as well as the lithology. So if we look over here to my right, we can see a fairly coarse or fairly thick bed of chert that if I actually go and take a measurement of is approximately 30 centimeters, whereas these shale beds are about 5 to 8 centimeters across. So we see that these chert beds form more coherent and thick beds relative to the shale. But in a second here, we're going to take a step back and look at a thicker zone of shale. But a big take home here is that we have two main lithologies. We have this chert unit with this sort of oxidized surface, as well as this more reddish brown shale unit, indicating that we're in a marine system. Okay, so now we've moved down the outcrop here to look at this really thick section of sort of chopped up and broken up shale. So here we can see on either side of me, there's the sort of yellow beige colored Claremont chert here with this really large interval of interbedded shale and chert that's now, as you can see, pretty broken up. And what I want to point out here is this is an example of a faulted structure. So this, as we discussed in lecture, is actually called a shear zone. So the rocks here have been broken up and faulted and sheared as a result of tectonic forces. And if I actually put my hand here, we can see an example of one of these faults cross-cutting this surface here. And you can see a few of these sort of inclined features that are cutting across the rock that are examples of the traces of faults on the surface. And we'll actually go up closer up the outcrop here to see a little small example of this deformation. But what I want to take you to take away from here is that this outcrop has experienced tectonic activity in the form of faulting, resulting in this jumbled, broken up area of chert and shale here. So what I want you guys to be thinking about as we're going through this outcrop is the processes that we go from a deep water marine environment in this place that was deposited horizontally to, as we move up section, we begin to see what are known as subaerial or continental type deposits. So what I want you to be thinking about is how these things are transitioning through time, because they're directly related back to the evolution of this area from a subduction zone to a transform boundary. And so what I hope that you guys take away from this is the understanding that we have changed environments and we're also changing where these rocks are being deposited. So just be thinking about these things as we're going up through this field trip. And as we discussed in the last section of this video, this is an example of sort of the scales that faults can take. So in that previous location, we could see sort of larger scale, meter scale faulting. Here we're actually looking up, as you can see from the scale of my hammer, a very small offset fault here. And we can tell that this is a fault because the beds themselves are slightly offset, but you can also see this rubbly fracture here, which is evidence of the rock actually being deformed and broken as a result of these rocks moving past each other. So again, this is something to be thinking about, of the forces at play here to actually rotate these beds up away from their original position to the position we see today. So part of the way we discussed about interpreting and describing the orientation of rocks is using the method known as strike and dip. So as geologists, there's a way that we collect this type of data using what's known as a Brunton compass. So this is a Brunton compass. It's a very specialized geologic tool that's used widely by field geologists, including myself, to actually get the orientations of these beds. So if we think back to our maps and structures lecture, we can think about the strike of this bed as the angle that this would make as if you were to drop this in water and the horizontal line this would make with the dipping surface. So in this case, we can see that the beds are actually dipping in the direction that's behind me. So if I was using right-hand rule properly, I would orient the strike such that the beds were dipping to my right. So in this case, looking in this direction, the beds are dipping to my right. So strike is actually in this direction, whereas the beds are dipping in this direction. So if I'm going to take a strike and dip, what I would do is open up the compass, and you can see here that it records an azimuthal direction as well as an inclination direction. And I would actually go up to the outcrop and take the orientation to actually get the strike, which I will report. as approximately 130 degrees. So that is approximately to the southeast in terms of the strike. And then the dip here is the inclination of the beds. Is approximately 89 degrees. So this is actually an overturned bed. So what we would do is actually take the supplementary angle, so we would go beyond 90 in this case. But the big take home here is that we as geologists will come and assess the orientation or the dip direction of these beds based on right-hand rule, which again, these beds are dipping nearly vertical, so it's actually quite difficult. But the slight dip is to the direction behind me. So according to right-hand rule, if the beds are dipping behind me, the strike has to be in the direction towards the road.